ask it if it's working. Can you see us?
Can you see us now? Okay, great.
Okay, I hope that the technique will work, and I might try to give you a short introduction into the technique. You see in the background the instrument with its two columns and the head, the normal head here, and the lateral head here. And you see the screen, and I will switch between screen and this camera that you can better see what happens on the screen. So at the beginning, when you define a measurement, where's this mouse? I don't see the mouse here. Here. No. No. You see on the screen the sample holder, and to the right the camera, and the two lines in the main menu. The upper one is for the analysis of the data. The second is for running the hardware. The first would be to define indenter. There's already a Berkovich indenter installed, so we don't need to do that. The second would to install the sample, and we have a set of sample holders available, so we can switch between the different holders and choose the holder you want to use. At the moment, we use the holder with 5 positions, which is the standard holder, and which also allows a measurement of the contact resistance between tip and sample. To change the sample, we have to go in front. You can see here the sample holder with 5 positions, and 4 of them are used at the moment. One is fused silica, one sapphire, silicon with an oxide layer, and aluminum. There's another sample holder where you can clamp larger samples, so tubes or other things, and fix them without gluing the samples. And we have also a heater, which is installed instead of the sample holder with an extended shaft, which is going inwards with a tip. You see here the contact for the contact resistance measurement. Now I install the holder again. So it's a stop, and the reproducibility of the installation is quite high, so plus minus 10 micron is normally possible. Now I go back to the software. We have to move to the original positions. You see here 2 circles. One green circle is for the camera position, and the other circle is for the tip position. We are now below the or above the with the camera above the fused silica sample, and we have an autofocus option where we can find the sharp surface automatically. It will switch on the camera and go down. This is the stage, and then it will look for a sharp image and has to adjust also the illumination. So now we have found, you see possibly some dust on the surface. We see point positions, which I should better see in black. And the next step would be to define an application. Here we have a lot of predefined applications. We have a fast hardness test where you can load, have a creep period, and an unload segment. By clicking one of the symbols, you get already a predefined application. This is the cyclic measurement. You can go to 20 cycles or what you want, and then you have more cycles. We can also choose a sinus-shaped loading and unloading, and we can use a fatigue test with slow cycles, or we can do fast cycles as well. So at the moment, I only want to demonstrate a fast hardness test. And we have to define also the positions. So we can make a row or a column, different number of positions. It's quite fast to define that. We can also add to a row a line and do this many times so that we can introduce any array on the surface. We can also have a regular array and as addition. So at the moment, I only want to do 3 positions in a distance of, say, 50 microns. Sorry. And the first shall be with a force of 100 millinewton and the second with 10 millinewton. The application is for all positions the same, so it uses the same time. Now, the last what we have to do is to start a measurement, but before I told you already about the clamp, which is blocking the lateral movement, and for a normal hardness test, we need to block it. Now we can press start, and goes now to the tip position. And everything is running automatically. First with an approach. There's a program, there's a time programmed when it shall start. I can skip that. We have the approach with a mechanical stage. It has a distance normally of 3 millimeter for security reasons. And there are different speed levels. So at the beginning, it goes fast, and then it goes slower and slower. So that it can detect the surface quite accurate, what happened now. Now the piezo element is used to retract the tip and go to the measurement position. And now the approach is done with the piezo. So this also is going slower and slower as closer it comes to the surface. And as soon as it has touched the surface, the measurement will start. So we have here the measurement curve. So this is the test with 100 millinewton. And creep time and unloading. All the tests will be collected in another window so that you directly can compare them. There also a time between the tests can be programmed. When it's longer than 1 second, then it's shown. And now the next measurement starts. So this shall be now with 10 millinewton only. So creep time again, and unloading will follow. You see in the other window that the loading curves agree quite well. After the end of the measurement, the tip goes up again, 3 millimeter for security reasons. Of course, you can magnify that to see it better. So anyway, we have still a small error at the 0 position that we can correct. So here it's automatic correction selected. Now it's done. And this is the window with the results. So here we have 72.5. this is slightly larger, maybe the calibration is not that accurate anymore. Okay, now we want to go back to the camera and have a look. Again, we use the autofocus feature. And we should see the indents nearly in the middle. So the first here is only from the approach with a mechanical stage. The next one is the indent with 100 millinewton, and we can put it to the middle of the image. And we can now switch to a higher magnification. So we have to correct the focus level. Now the illumination is a little bit influenced by the light in the room. See now. So you see now the indent. And we can also measure, so it's quite small. It's about 4 micron. And if we go to the next position, we see here, possibly or not, a very small indent of the 10 millinewton. So this is demonstrating the resolution of the optics. We can even double the size. So here, this is in a size of less than 1 micron that you even can resolve in the optics. So next, I want to show you a scratch test. And this I want to use to demonstrate how easy the tip can be changed in the instrument. So I switch out the camera and I use now the indenter menu and can open a calibrated function. Is this, and this is a spherical tip. So we can also use a shaft extension, but it's not necessary now. And we go to the exchange position. This is at the back that I have access to the tip. And now I switch to the camera image. So you see here the tool that we use for the tip change. You can use the fingers to screw the tip or unscrew it because the head is so robust that you cannot damage it with this tool. So then we use a normal tool to unscrew the tip. I don't know where the tip is. Sorry, I don't know where the other tip was. So I will install the same again. But you can see how it works. So I screw it. Put it upside down and screw it in the instrument. So that's it. When you have changed the tip, we normally have to adjust the distance between tip and camera again. So I have to read the Berkovich again. And we go back to the last position below the camera. So we use distance calibration. It's a let's go to Indenter. We need a distance calibration. The camera is a prepared software module. And I switch back to the software. So you see that. And we choose force for the indentation. And now everything is running automatically. So it will make the indent first by approaching the surface with a mechanical stage. Then it will immediately do the indent, but without measurement because you don't need it. So last 50 micron. So it has found the surface. And now the force is applied, 500 millinewton. It goes back to the camera position and will focus the surface. And you see the indent is now here. It's a bigger one with 500 millinewton, and we have to put the cursor in the middle of the middle of the indent and press finish. And then that's it. You see the correction of the calibration, and that's it. So now we can do the next measurement, and for that I want to go to another sample. Here we simply can right-click with the mouse and say go now to position number 4 on the sample holder. I think this was, no, it was 5. And we'll find the surface again. This was an aluminum sample. No, it was a wrong one. I want to go to position 4. It's a silicon oxide layer. I can move by hand as well. Try to refocus again the surface. So here it's out of the search area. So this is the surface. It's a bit not too much to see. What I want to do is a scratch test here. And for that, we choose the other application, scratch. Because we have a sharp tip, I use a small force of 50 millinewton. we use a pre and post scan with a small scan force of 300 micronewton, and the distance may be 250 micron. Speed is 10 micron per second, and that's it. And we need only 1 point for the scratch and 1 point for the approach with a mechanical stage. We can also drag the point in the optics with the mouse if you want. And now I go back to the indenter and we start the test. So in this case, we have to close the clamp. And the first, after the approach, will be that we make a measurement without contact against air to measure the spring force of the holding springs of the lateral force unit. But before that, we do the mechanical approach. So this sample is a little bit deeper than the previous one. So it will not find the surface at 0, but you will see maybe 200 micron or 70 micron deeper. Now this is the measurement against air. Oops, was a small vibration at the beginning. So here it's only the vibration is not disturbing the result. It's only use the slope of this curve to get one spring constant. We don't need the details. Oh, here was one approach problem. I will try again. So now it should find it close to 0, the position of the surface. That's true. It will do the lateral test again. Okay, what's this? We have a problem here. Maybe it has to do with the approach speed. I will delete the waiting time. So let's try again. The 0 point is a bit shifted at the beginning or due to the vibration, but this doesn't matter. So now it works. This is the scanning force, used 300 micronewton. And this is the pre-scan of the surface to measure slope and roughness. After that, the scratch will start at the end of the scan range, going back to the start position. So the maximum force will be applied at the starting point. And we have an additional scan length outside the scratch of about 20 micron defined on both sides. So you see on the fluctuation of the curve already that there's some fracture in the coating. 50 micron was the maximum. Of course, we can also program a scratch with constant force. So now after unloading, again, a scan is done. It's called post-scan, to see the remaining plastic deformation after the scratch. And when this is ready, it will show the scratch results, because this curve here is difficult to understand, because it's the slope and the indentation depth in the same curve. Now you see the scratch results. You see a slope of the pre-scan, the gray line, and you see the calculated slope is only 0.12 degree. We can correct this. You see the brown line is the plastic deformation, and the red line is plastic and elastic deformation. We see the blue line as the lateral force. We can convert this to friction. So we have a relatively high friction due to the strong plastic deformation. You can also see the longer force as a linear curve here. And with the bar, we can detect any critical point. In this case, for a sharp tip, it's not possible because we have no starting point. The plastic deformation starts already at the beginning. And we can now have a look to the scratch in the camera. This is the last of my presentation. You see the scratch. So the indications give you the begin. It's here and the end of the scratch, and this is the additional range outside the scratch lengths where the force is reduced to 0, and this is also the range where the scan was done. So the newest one is that we can also insert a graph where you see the curves in the scratch and you can directly compare this with the scratch track in the optics. So, of course, we can, if you don't see that, we can invert the colors, or we can measure here in the graph where which force was at which position. Thank you for the attention.